Hi there, everybody. Hope you have had a good start to your morning so far. And we are going to get ready now as we dive into lesson 4.3. We're going to talk about the significance of the second derivative. We spent so much time on the first derivative and how we can talk about increasing and decreasing and critical points and extreme values from the first derivative, but the second derivative is really important as well. So what we're going to introduce today is that second derivative, its importance. We're going to introduce a new vocabulary word called concavity, and we'll also talk about finding key parts of a graph called a point of inflection. So that's our takeaway from today, concavity and points of inflection. Concavity has to do with the bend of a graph, the particular arc of the curve, and whether that arc would be what we call concave up, which would be sending things out and away from it, maybe up into outer space, or this example of a satellite dish is what we would call concave up. Anything that would bounce off of it would bounce up, and so that is considered concave up. Something that would be concave down would be if you bounced off of the interior of that, you would be bouncing down instead. So concave up versus concave down. Here's maybe a better way to look at it. If you look at the x cubed graph, as we trace x cubed, let me try and do that here. I'm trying to use a yellow highlighter to trace that. As we come through quadrant 3, up towards the origin, we are on what's called a concave down section. And then at the origin, a distinct change happens and the curve bends differently and it becomes what's called concaving up. And so from that point forward, moving away from the curve and continuing up into quadrant 1, we have what's called concave up. So you have concave down, if you can see the bend of that curve, versus concave up. What it basically means is having to do with what the slope is doing. The slope is getting less than what it was before versus the slope getting larger than what it was before. So in a concave down section, the slope is decreasing. In other words, it's getting less steep. You can see it's starting to lose its bend. It's starting to bend and get more towards, as it approaches 0, it becomes horizontal. And then in a concave up section, the slope is definitely increasing and the graph is getting steeper. So when something is concave down, the slope is decreasing. When something is concave up, the slope is increasing. We can tell concavity based on the second derivative. So we're going to use words like concave up. And concave up means y prime is increasing. Or we'll use words like concave down, which means y prime is decreasing. So the slope is increasing or the slope is decreasing. And we can tell it is concave up when the second derivative has positive values, and we can tell when it's concave down when the second derivative has negative values. So we're going to see things that are pluses in the second derivative compared to things that are minuses in the second derivative. That will be the connection to concave up versus concave down. So the same plus minus charts we've been using for first derivative, we're going to use for second derivative as well. Graphs have many points of inflection, and a point of inflection is just where the point where the instant where the concavity changes. Let's take a look at this first graph. Here is a point of inflection right there. That point is where the graph started concave down, So this section of the graph is what we call concave down. And then switching to concave up. But then it switches back. So we have another point of inflection where it switches, the graph switches back to concave down. And then another point of inflection where it switches back to concave up again, where the slope is then increasing. And then it'll change to the slope decreasing. And so we have many points of inflection on this particular graph. You can see the pattern as the concavity continues to change. On our second graph on the upper right-hand corner, our points of inflection are happening as well. So these points of inflection happen right here. Concave down, switching to concave up. Switching back to concave down, switching back to concave up, and then switching again. So we're going to have many points here where the concavity continues to change as the graph continues to wiggle its way up through quadrants 3 and then into quadrant 1. The one at the bottom is your most basic. Okay, that concavity changes about right here. And all of this section is concave down. The slope is decreasing. It's less, every point you go, the slope is less than it was before. The slope even changes to be negative, but it continues to be less than it was before. Then at that point of inflection, after that, the slope is not less than it was before. The slope is more than it was before, and it continues to be more as the slope turns the corner and starts to increase. So we call that the point of inflection. Now we find those points using the second derivative. So that's our definition. The point where the graph of the function has a tangent line, that means it's differentiable. And if it's differentiable, it means it can't happen at a corner or a cusp. All right, so you can't have a point of inflection at a corner or a cusp. Point of inflection is only going to happen where the function is differentiable, and then it also indicates a change in the concavity. We can find these every time we take our second derivative and start by testing it equal to 0, much like we did with the first derivative. So if we want to find the points of inflection for a cubic graph, we're going to find the first derivative. So we'll be looking at 6x squared minus 28x plus 22. So that's our first derivative. And then we're also going to find the second derivative. So that would give me 12x minus 28. This second derivative is what I set equal to 0. And then when I solve that for x by adding 28 to both sides and dividing by 12, so when we simplify, both of those can be divided by 3. So we'll have 7 by 4, so we'll have 7 over 3. So this is a candidate for an inflection point. Now, it's not for sure an inflection point. It is a candidate for an inflection point. So the way we're going to tell if it's going to be an inflection point is we make a interval chart before and after. So x, things that are less than 7/3 and things that are greater than 7/3. And we're going to check that in the second derivative. So I'm going to pick something less than 7/3. I'm going to pick 0. But I'm going to plug it into the second derivative, not the first derivative. I will plug it into the second derivative. So I'm going to have 12 times 0 minus 28. That's going to give me a negative value. Then I'll pick something that is greater than 7/3. So I'm just going to pick 5. So I'll check my second derivative value there. So 12 times 5 minus 28. That'll be 60 minus 28. That would be positive. So now I know for sure that x equals 7/3 is indeed an inflection point, because I've shown it was a candidate and I've shown that the concavity changed from negative to positive at that spot. Let's find inflection points for sine. Now we could do that probably, you can think about sine, how it wiggles its way, it oscillates. So sine's going to have lots of inflection points. So we want to find sine's first derivative. First derivative would be cosine. We'll find the second derivative. Second derivative is negative sine of x. We want to set that equal to 0. And there are going to be multiple candidates. 0 is the first candidate, but so is plus or minus pi. That's another, those are 2 more candidates. Plus or minus 2 pi, those are more candidates, etc. So these are all candidates for points of inflection, because the second derivative is equal to 0 at all those places. So I want to check these points of inflection. So I'll do some as a sample. So we'll check from negative 2 pi to negative pi. And then we'll check from negative pi to 0. We'll check from 0 to positive pi. And then from positive pi to 2 pi. And I think we'll get a good idea of how things are going to be happening here. So remember, these are candidates for points of inflection, but they are not true points of inflection until I've checked the derivative. So we want to pick something that's between these values. So I'm going to pick a negative 3 pi over 2. So I want to know, what is the negative sine of negative 3 pi over 2. So this negative sine of negative 3 pi over 2 is a negative number. It's negative 1. I'll check negative pi halves. So negative sine of negative pi halves. The sign of negative pi halves is already negative, so 2 negatives make that a positive. So now I see a change in the concavity. So this started as negative concavity, changing to positive concavity. Between 0 and pi, I'll take the negative sine of positive pi halves, and that is a negative number. And then finally, I'll check the negative sine of 3 pi over 2, which is negative 1, so a positive number. So we're seeing our concavity change over and over and over again. So all of these are proved to be points of inflection. So we're looking at all points of inflection. And so we would write it like this. X equals k pi are points of inflection. And then k stands for integers. So this would include plus or minus 1 pi, plus or minus 2 pi, plus or minus 3 pi. And we know that this is true anyway because we can picture that sine just goes up and down and oscillates. So we have lots of points of inflection popping up every time the concavity of the sine graph changed. Let's find the points of inflection for a pretty simple graph. That would be y equals x squared. This is a parabola. So you want to take your y prime. Your y prime is going to be 2x. And then we're going to take our y double prime, and our y double prime is 2. We take our second derivative and we set it equal to 0. But 2 can't be equal to 0. So what does that mean? It means we have no candidates. There are no possible points of inflection. Which means there's no possible way for the concavity to change. And that should confirm what you know about a parabola. This parabola is facing upward. That parabola has only one kind of concavity. It is always concave up. It's impossible for there to be a change. There's only one vertex of this parabola. And so there are no, this one is always this parabola. So the parabola y equals x squared is always concave up. So you would say there are no points of inflection. Okay, so no points of inflection exist. And so that confirms, the calculus confirms what we already kind of knew visually. How about finding inflection points for something that's exponential? Does this have points of inflection? Well, let's take a look at it. So let's take a look at what y prime would be. So this is an exponential graph, which means its derivative has those 3 parts. So part 1 is 2e to the negative x squared. Part 2 would be linear. And part 3 would be negative 2x. So that's going to simplify to 2e to the negative x squared and 2x. Linear is 1, so that part doesn't have any significance for this problem. Now I want to move on to the second derivative. Now the second derivative is going to need the product rule because I'm now multiplying 2 different types of equations together. I have 2x and I have the exponential piece. So the first part of my product rule will be 2x. The second part of my product rule is going to be 2e to the negative x squared times linear times negative 2x. So that's the first part of my product rule. Plus 2e to the negative x squared, and then times the derivative of 2x, which is simply 2. So we want to simplify this if at all possible. So we know linear is going to be 1. So for this first section, we're looking at negative 8x e to the negative x squared. And then plus 4e to the negative x squared. You should always write this in factored form. If there's something in common that you can pull out, you should. And so I noticed that there is an e to the negative x squared. That's common to both of those terms. But so is there the coefficient of 4. So that would leave me with negative 2x plus 1. Now what am I going to do with that? Remember, I'm going to take that second derivative and set it equal to 0 to see if I have any candidates. So that means I have 4e to the negative x squared is set equal to 0. And so is negative 2x plus 1 being set equal to 0. The first one has no solutions. 4 times e to the negative x squared would never be equal to 0 because an exponential never touches the x-axis and would never be equal to 0. The second one does have a solution. The solution is x equals half. So this is a candidate for the point of inflection. Doesn't mean it is, but it's a candidate. So I'm going to check all values of concavity that are less than half, and I'm going to check all values for concavity that are greater than half, and I'm checking this in the second derivative. So the easiest number for me to pick that's less than half is 0. So that's going to give me 4e to the 0 times negative 2 times 0 plus 1. All of that value together, e to the 0 is 1, 0 times negative 2 is 0, so this is going to end up to be a positive number. So I have positive concavity before for all values that are less than half. I'm going to pick a number that's bigger than half. So I'm going to pick 1. So that will give me 4 times e to the negative 1, negative 2 times 1 plus 1. Now e to the negative 1 is 4 over e. That's still positive. 4 is positive and e is positive, so that is still a positive number. In the parentheses, we'll have negative 1. So I've got a positive 4 over e times negative 1, so that would be a negative concavity. So this graph is going from positive concavity to negative concavity, and so I've shown that x equals half is proved to be a point of inflection. And it's because the concavity changes. If you can't show that the concavity has changed, you haven't found an inflection point at all.